So Friday is the first exam. And the topics are everything up through linear interpolation. So the stuff we started doing last time about incompressible materials and ideal gas law, that's not going to be on there. And so today, since this is a class with just a lot of equations you're trying to fit together, I'm just planning to go through kind of an outline of what we've covered with all the equations. Okay, so first, the problems related to this stuff are what I call the introduction. These are the problems under introduction. And let's see, there were kind of two main things that were brought up in this. The first one was talking about pressure. And so with pressure, remember that the definition of pressure is the force applied perpendicularly to a surface divided by the surface area. And so you can always go back and forth between pressure and the force applied using that. And we did a few problems like that, remember, where you have to calculate like a total force applied to a wall of something by a pressure. And then second, we used an equation that said for fluids, so fluids are liquids and gases that are continuous and at rest, and those, so it's easy to find counterexamples of fluids that are not continuous or not at rest that don't satisfy this equation. But as long as they're continuous and at rest, we know that the pressure at the lower height is equal to the pressure at the higher height plus the density of the fluid times G times H, or the depth or whatever. And we use this for a bunch of calculations involving like things under the surface of water or whatever. You also can use this equation for two common like types of instruments for measuring pressure. The first one is a barometer. Well, I don't know which order I did. I think I actually maybe did a manometer first. Let's do that first.
Good memory. Right.
And so a manometer is for measuring the pressure in a confined gas.
Fluid or gas?
More often it's a gas. It has to be because you have to have a liquid here, and that liquid can't mix with the pressure that you're trying to measure. So usually this is a gas. I don't know. There's probably other cases, but so this in here is a liquid, and you have a height h here. This end is open, so there's an atmospheric pressure there. And so the, this here is the gas pressure. And so the pressure in the gas is equal to atmospheric pressure plus the density of the liquid times G times H. And then the other type of pressure measuring instrument is for measuring atmospheric pressure. That's a barometer.
Super quick
Yeah.
question. So like the diagram above,
Mhm.
regardless of the shape of the glass tube, as long as the water on the right side is flat, your force is applied perpendicularly.
Yeah.
Okay.
Mhm.
So the tube could be like crazy.
Right. And does it have to be perpendicular? Well, I guess it's just perpendicular because that's how the liquid will settle.
Yeah,
Yeah,
exactly.
right. Yep.
Okay.
Okay, and then for a barometer, this time you don't have, so you have a liquid in here that's open to the atmosphere. And this time you don't have an open end in the tube. You have atmospheric pressure pushing down. That's happened twice this semester.
Really?
Yeah.
And now the backup will kick on.
So a barometer, so the difference is with a barometer compared to the manometer, the top of this column isn't open. And so you try to use a liquid that, that has, at this temperature and pressure, a low vapor pressure, yeah. And so if it's close to zero, usually, then the pressure of the atmosphere is equal to basically, this is the vapor pressure, which is usually about zero, plus the density of the liquid times G times H.
And the vapor pressure is like how much pressure is caused by the evaporation?
Yes, that's right. Yep. And so there's some like equilibrium amount of molecules of that liquid that's in vapor, and that's applying a pressure to the surface, but it's low if, in one of these that's working well.
Like mercury is so dense that it's not evaporating readily?
I don't know. I don't know why. I mean, I suppose with any liquid, it has to do with the temperature and pressure, really. But at room temperature, yeah, I mean, I guess mercury is just very far from boiling, I guess.
Yeah.
Okay, so that is pressure. And then the other thing we talked about in this intro is something that's going to keep coming up through the whole class, and that is work, mostly the work of expansion. So let me break this up into the work of expansion. And this is really only useful for gas. You never really calculate the work of expansion of a liquid because it's so small, it's so close to incompressible. And this is equal to the integral from the starting volume to the ending volume of P dV. And remember that this follows the first law sign convention. So the sign that you get from this, you can plug right into the first law always. In order to use this, so to compute this integral,
Any reason you don't do like p parentheses v to signify that it's p as a function of v?
Well, I mean, it's true no matter what. So it's true whether that pressure is known as a function of volume or not. So I guess that's why. But yes, in order for it to be useful to us, without going into a lot of elaborate like partial differential equation type stuff, that's just what I was about to say. Is that to compute it, you want pressure. You need pressure to be a function of volume or constant. Those are the two cases we're going to see. So to compute this integral, you need pressure as a function of volume or pressure constant. And one of the cases, so if you're lucky, pressure is constant, then it's super easy to compute. If you're kind of lucky but a little unlucky, then you have something like this exponent relationship between pressure and volume. And you have to go through all the exponent and log rules and stuff to figure out, to calculate what that function actually is. Okay, so that's the biggest thing that's going to keep coming up with work. But remember that work also is used to represent any kind of electric power coming in or out. So anytime a problem discusses electric power or electric power generation by the thing, that goes into the term for work. And then also rotating shafts is also represented by work. Oh, this is called, by the way, a polytropic process. And it's not a material relationship. It's just kind of an experimental relationship. You happen to have done some tests on pressure and volume in the setting that you're using, and you notice they have this exponent relationship. And then the second overall category is the first law of thermodynamics. And so far, we've only talked about this in closed systems. The next topic we're going to get into is I'm blanking on the term, but fixed volume systems, where we're looking at a volume of space as material flows in and out. But closed systems is like you're looking at the same amount of material as it does whatever it does. Did you see it in your notes?
What it controlled volume?
Control volumes. Yeah, that's what we're doing next.
I knew I saw it.
Yeah. Okay, and so this says the change in energy is equal to Q minus W. And really, if I had to put my finger on the number one thing I'm trying to make sure that you have straight on the first exam, it's just this sign convention being right. Okay. So the signs are everything. And so Q, if this is positive, this is heat into the system, heat into the system, and W is work out of the system. And E is the kinetic energy plus the potential energy plus the internal energy. And these two, assume these are constant in this class, unless you have reason to believe otherwise. You know, unless you're given reason to believe otherwise, like you're given changes in height or changes in speed or something.
So all we need to know is that a change in, say, temperature would have happened for us to know that we should calculate it. But if we know that it wouldn't have happened,
With the kinetic and potential energy?
not to
Yeah, I mean, you can assume that there's always, the internal energy is always something to think about, you know,
for sure.
because we're always, I mean, pretty much we're going to have changes in temperature, like work done or heat added or whatever. Like, so energy is going to change usually. But, you know, we're usually just not dealing with systems that are changing their speed or changing their height. It's just less common that we're going to do that. So if it doesn't mention speed, doesn't mention height in some way, then we're just going to assume that those stay constant. There are two simplification terms that, I mean, this really is more something coming down that's on its way, but these are useful to keep in mind anyways. I know if I've mentioned this so far, it's only been in passing, but one is anytime you hear the term steady state, that means that the change in energy is zero. It really means that any property stays constant. And another way to say this, if you're dealing with the differential form of the first law, it also means dE dt is zero.
So would that mean there's some direct exchange between work and heat then?
Well, yeah, it means they have to be equal to each other. The mechanism for that, how that happens, you don't know. But this is
efficient.
what?
Completely efficient, no.
So, well, you don't know that really, but you just know that, like, say you're taking the temperature and measuring the pressure and stuff as this thing goes, and you just happen to notice, like, okay, it's not changing anymore, you know? And so then you can make that assumption. Bless you. The other simplification is a cycle. A cycle is kind of similar, except steady state means there's just no changing of properties as time goes by. A cycle, the properties can change. It's just, you know, that if you're looking at comparing two parts to the same points in a cycle, you know, the repeating points in a cycle, all those property values have returned to be the same. So this one also means that the change in energy is equal to zero, but it doesn't mean dE dt is equal to zero over the whole thing. Okay. Like a cycle, an example of a cycle is like the cylinder in a motor with a piston moving up and down. There's a lot of stuff going on, and those properties are changing. But if you're always just comparing the point where the piston is at its low point to the next time the piston is at its low point, and nothing changes between those instants, you can use this fact. Uh, Now, the other thing we've talked about is the differential form of the first law. So d dt is equal to q dot minus w dot. Q dot is the rate at which heat is added to the system. And W is the rate at which work is done by the system. This is kind of a helpful way to think about this stuff. So there are times when you're like, you see a problem and you're not totally sure whether you want to use this form of the first law or whether you want to use the differential form of the first law. Here's some things to kind of look for that'll tell you, yeah, I want to use the differential form. So let's say here are some indicators that you want to use the differential form. So the first one is if you're given energy stuff in terms of watts, that's joules per second. And so that, that's being given to you in terms of a rate. Second, if there's a time dependence on the variables. So if you're given variables with T as, you're given, say, work or heat with T as a variable, then usually you're going to want to use the differential form. So time dependence. Variables. And then the last one is anytime you're combining this with the heat transfer equations, you're going to use the differential form. Okay, and then second, I'll give this its own category, is using the heat transfer equations. This is the most common reason that you would use the differential form. And the main thing that you want to remember going into using the heat transfer equations is you can't trust the signs coming from the heat transfer equations. So if you're going to use these with the first law, you have to just think that through on your own. What direction is heat being transferred? Okay.
That's all three of them.
All three, yeah.
And so we just disregard the equations?
Yeah. Just disregard the signs coming from, just think of those as giving you absolute values, or take the absolute values and just don't even worry about the signs of it. Then just think like, okay, so I know that I know that this part is hotter than the system I'm considering, so heat's going to be flowing into the system, and then come up with the signs for the first law that way. Okay, do you know what I mean? Like, so if
Just
you're
based on the problem.
yeah, just based on the direction of,
Yeah.
I mean, you know, heat is always going to be flowing from high temperature to low temperature. So if your system is inside a room that's a higher temperature than the outside, then you know heat is going to be leaving your system. And so then you know that your Q has to be negative when you use it in the first law. Okay. So I'll write down these equations. The first one says, the first one is conduction. And it says Q dot is equal to negative kappa times A times d temperature dx. That negative sign, just forget that's there. And we're always going to be assuming a linear gradient of temperature with respect to distance. And so you can always just think of this as the change in temperature divided by the total distance in this class. The second one is radiation. And there's two of these. One says Q dot is equal to the emissivity times the Stefan-Boltzmann constant times the surface area times the temperature to the fourth. This is just the rate of heat emitted. You know, emitted only. So this is not very useful with the first law.
We're mostly doing like absorb.
Okay, let me just write this and then I'll answer that. So it's not useful on its own. With the first law. And the reason is that we care, for the first law, we care about the net change in heat, you know, the net absorption of heat by the by our system. And so this is only telling one of the two directions. So this is saying, okay, we're losing this much heat, but it isn't saying anything about how much heat is coming in. So for the most part, unless you're given more information than that, there's not really any use for this in the first law. But the second form is useful. It just isn't. This is a law of physics. So that's the cool thing about it. It's always true. The problem is you need more information for it to be useful. This one is always useful, but it's not a law of physics. It's for like a special case that the total Q dot is equal to emissivity times Stefan-Boltzmann constant times the surface area times the quantity temperature of the body to the fourth minus, it doesn't matter what order you put these, but temperature of the surrounding to the fourth. So this one is useful for the first law. But it's only applicable for a smaller body surrounded by a larger body. So this one does give you a net heat transfer. It's just you can't always use it. And then the last one is convection. And this is the one that's sort of least like a law of physics and most just curve fitting something to your specific process. And this says that Q dot is equal to some constant that you found experimentally times the area of the material that's exposed to the fluid. Bless you. Times the difference between the temperature of the body and the temperature of the fluid. So this is an experimental constant. And this A is the surface area of the body that's exposed to the fluid. Okay, and then the last one, I don't have too much to say about this, is material property relationships. So remember that, let's see, I think really all you have to remember at this point is in the vapor dome, this side is a saturated liquid. This side is a saturated vapor. Inside the dome is a mix of those two things. This is the critical point. In the tables, on those two saturation lines, and so at saturation, and that means on the saturation lines and inside the vapor dome. You only need to know one property to look up any other property. Give me 2 more minutes. Outside the vapor dome, you need 2 properties to look up any other property. And then the last thing that we talked about was linear interpolation. So to use this, you have to remember if you're using this with anything in the vapor dome, you have to be ready to use the quality. So the quality is the mass that's vapor divided by the total mass. And if you have the quality, then for any property, the property of your specific mixture is the quality times that property for the saturated vapor plus 1 minus the quality times the property for the saturated liquid. And then for linear interpolation, we have F is approximated by F at x1 plus F at x2 minus F at x1 divided by x2 minus x1 times x minus x1. And you could write this as we're approximating this function value at x. And x represents a property that we know, and f is the property that we're trying to find at that corresponding point. Okay, and so you'd use it once if you're at a saturation point. You'd use it 3 times if you're away from a saturation point. And that's about it for the test. Anybody have any questions about that? Okay. All right. Well, see you Friday.